Hello, this video is going to be a walkthrough of the 2016 practice ASBOG exam that's published by the National ASBOG. And since the exam is in the candidate handbook and is free, I think it's all right for me to do this. I got this idea from another channel called Geologic, who has some great ASBOG related videos that you should check out. I'll leave a link in the description to his channel. He answered a couple of questions that come from this exam, and it gave me the idea that, you know, while I'm in quarantine because of COVID-19, this would be interesting to do and would give me an opportunity to stretch the brain muscles and also have some fun with geology. So there is likely more than one way to reach an answer, as is usually the case in geology, and I already know that from watching GeoWes's video that I would have approached a few of those questions a little bit differently, but nevertheless, we came to the same answer. So I'd appreciate any alternative methods in the comments. And if I make a mistake, I'll put an annotation on the screen and probably make a comment in the description. But in any case, before I got started on doing any problems, I wanted to go over a few questions that I'm going to be thinking about in the back of my mind as I go through this exam. So hopefully, let's see. How does this work? There we go. So what is the question really asking? Sometimes I think ASBOG questions are heavily shrouded in jargon that is really intimidating, or maybe is phrased in a way that's a little bit funny to us. And that if we really just get to the main essence of what the question is asking, the answer just seems to come a lot more quickly. The next question I ask myself is the question requiring me to recall some specific information, or is there something in the question that's going to make it easier for me? So going back to wording, what they're trying to emphasize by asking that question, what kind of skill or concept were they looking to test when this question was created? And the next one would be, do the answer choices all have something in common, and what differentiates them? And then what do I know? Sometimes I like to not look at the answer choices before I dive into thinking critically about the problem. I think that oftentimes gives me a much more genuine answer, and I feel a lot more confident when I come up with the answer choice without having seen it. But again, whatever method works for you for passing the exam, that works for you. Do remember this is a timed exam, but what I'm going to be doing is looking at each problem, and if I feel necessary, kind of expounding upon why certain question answers are wrong and why the one I chose I felt very confident in. And that's a go-to method of mine as well, is proving all the other options wrong. So I feel pretty confident that I'll get a high score. But in any case, let's go ahead. One thing I did want to mention, just because I haven't gotten used to doing a lot of talking during the coronavirus, I'm probably going to do the first half of this exam and then do the other half later. And I'll just upload 2 separate videos, and I'll probably link that or something. But I can imagine that after doing 20 of these and commentating, that I'll be very tired from talking and need a break. But in any case, so let's go ahead and get started. So like I said, I'll link this PDF in the description. It's free online for anyone to view, so don't think I'm doing anything shady. Okay, here we are. So make sure that you're looking at the the fundamentals part and not the professional geology exam. So let's see, let me get my pen. All right. When water contacts pyrite at the Earth's surface, the runoff is commonly what? Well, I immediately think, when I think of pyrite, I immediately think of its chemical formula, thanks to mineralogy, FeS2. So it's an iron disulfide. And I remember, or if I didn't remember the chemical process of the weathering and breakdown of pyrite, as it's introduced to oxygen and water, you might just be familiar with acid mine drainage in general, and you might remember that pyrite is a big component of that. And so you're dealing with a lot of acidic runoff. Or, the route that I'm going here is I'm thinking about pyrite getting added to oxygen and water, and how that results in sulfuric acid, so H2SO4. All right, and I remember, and this is beyond the scope of this exam, but just kind of explaining myself a little bit further, that I remember that the breakdown of pyrite is a 4-step oxidation and reduction process that ultimately leads to acid mine drainage. But like I said, that's beyond the scope of this exam. And because we know we're getting more acidic, or at least we're producing an acid especially, we can be pretty confident that A is our correct answer. All right, we'll move on. What is the correct order of the ages of the units from the oldest to the youngest on the geologic map in figure 13? So before I really even get looking at this structure, I'm going to think about what I already know. So I remember that structures that look like this, they kind of make this A shape, that these are antiformal. All right, and that's not to be confused with an anticline, which says something about the ages. Well, right off the bat, we're being asked about the ages, so we don't have any information to confidently say, oh, this is an anticline, but we can say, okay, it is making this convex up shape that's characteristic of an anticline, or an antiform, especially right now. And then in another color, I know that structures that look like this, kind of poorly drawn, but I'm not an artist, these are called synformal. Oops. These are synformal, and that's because they have the structure of a synform, or a syncline, excuse me, and they have that convex downward appearance. And so right off the bat, we see that we have this antiformal structure. We see that we have limbs that are dipping away from the core, which is a characteristic of an antiformal structure. So let's go ahead and look at our answer choices and see if there's something that will fall out that maybe we're not immediately seeing, because this is a timed exam. We're trying to work smarter, not harder, for now. So what is the correct order from oldest to youngest? So option A, they're saying is the oldest, FO, DI, PM. So they're saying that the younging direction is this way, away from the core. So I remember that antiquity in the middle is how I remember that the older units are in the core of an anticline. So A is saying that this is an anticline. And I think that's a really good choice. I do. And if I was in a really big hurry, I would go ahead and probably just choose that answer. But for the sake of this walkthrough, I'm going to go ahead and look at the other options and see what I can see from the rest of the options. So This is D is the oldest, MO, FO, AA, and then PM. So this is saying that the youngest unit and the oldest unit have a contact with each other, and that, So we have to remember that our original principles of geology, so original horizontality, lateral continuity, they still exist, and we need to apply them in our thinking. It may have been a while since we last thought about those principles, but they still exist. We still have to think about them. So that, in my opinion, makes me confident enough to say I can immediately eliminate B. Okay, so looking at C, PM is the oldest, DIMO, FOA. So C is the exact opposite of A, and they're saying that the oldest unit is out here and that the youngest is inside, is in the core, so the young direction is inward. That doesn't, our data doesn't support that conclusion. Our data suggests, again, this is anti-formal. So unless we had an anti-formal syncline, which I don't think we do, there's the principle of parsimony, that the most simplest explanation is the one that's probably most correct. And so what this probably is this is an anticline, this is a syncline, and they're trying to differentiate, or I guess weed out the people who forgot which way anticlines and synclines go. I think that's a reasonable explanation. So we're also going to go ahead and mark this one out. D, PM is the oldest. DI is the youngest. So again, principle of original horizontality, that just doesn't make sense geologically. So we can be pretty confident, change my color, that A is our correct answer, that it's anticline. All right. Moving on to the third question. So in an aeolian sand aquifer, hydraulic conductivity would be expected to generally what? Increase upward, increase downward, be uniform, be the lowest in the middle of the unit. So it sounds like they're testing our knowledge of deposition and sorting characteristics and aquifers. So we know that we're dealing with wind-blown sand-sized particles. That's what aeolian means, is wind-blown. And we have sand, and we know that the sand is being used to hold and transmit water as an aquifer. And we're being asked about any trends that we might see in how well that water will be transmitted throughout that aquifer. So we know aeolian deposits, they tend to be well-sorted particles. So I'm going to write that down just for instructional purposes, I suppose. Well-sorted. So we know aeolian deposits are well-sorted, and they're small enough to be carried by wind. And so hydraulic conductivity is referring to how easily water is being transmitted. And hydraulic conductivity is a property of the porous media and is influenced by a few different things. So things like grain size. Oops, I didn't give myself enough room. Grain size, what else? Grain shape. And sorting. So we know that this is wind blown, it's well sorted, it's worn and well rounded. And so it's probably going to have a high porosity and probably a high permeability as well throughout. We don't have any real reason to consider any variation. So A and B are considering variations. We're going to go ahead and just mark those out. And D, be lowest in the middle of the unit. Not any real reason to consider that. C, be uniform is our correct answer. Okay. 4, which of the following characteristics would likely be composed of sediments with different grain size and sorting characteristics? So different is the key word here. So it looks like our answer choices consist of sediments or in like structures, and we have to identify the different sorting characteristics and grain size characteristics associated with each of them. So let's see here. Outwash plains. Some people call these sand doors, if that's helpful. So with outwash plains, we generally see fine grain sediment that's usually layered. How do I want to do that? I'll just say layered, I guess. Layered, and then in moraines, those are formed of till that is unsorted. And so usually like you have class of large class and really small class. It's just debris that's dropped from a glacier. So, okay, these seem very different. And so that very well may be our answer, but let's go ahead and entertain the other 3 options and see what we can get out of them. So an esker and a kame. So both of those are glacial features, and they, if I remember correctly, both of them are made up of sand and gravel. And usually those deposits are stratified. So it looks like these are pretty similar. So we'll go ahead and not delete, but eliminate those from our options. Tuff and tephra, they're both volcanics and are made of ash-sized particles. So those are very similar. And then Barkhan dunes and parabolic dunes, those are both Aeolian deposits, Aeolian sand deposits. And like we saw earlier, those are well sorted and well rounded. So very similar. So it looks like the one that's most different is A, outwash plain and end moraine. Okay. The 5th question, it has been determined that a prospective strippable reserve contains 1,000 acres, where 1 acre is equal to 43,560 square feet of lignite in beds averaging 20 feet in thickness. Assume specific gravity of 1.28. What is the reserve in tons? So something really important here that we need to highlight is that it wants our answer in tons. I'm not sure where everyone else would have started, but perhaps you may have gotten to the end with units other than tons, and you wouldn't find your answers among the answer choices, which is always a really defeating feeling. So it's good to know what you're working towards, especially if you're having to do some tedious dimensional analysis. Eventually, seeing that you're working towards the correct units helps you realize that you're doing your math correctly. So how I would start this problem, I'm not sure if I have enough room, but we'll see. How I would start this problem is I always am going to start with what I'm given. So I'm told that I have 1,000 acres, and I'm told for 1 acre is equal to 43,560 square feet. So I'm just going to convert what I have into square feet. So for 1 acre, oops. All right, so when I do that math, acres cancels out and I'm left with square feet. And so that just gives us a really big number. So 43,560,000. All right. So we're told that they average in thickness of 20 feet. So let's go ahead and make this cubic feet by multiplying by 20. And so what we get when we do that calculation is 871,200,000 cubic feet. All right, since we have that answer now and it's really large and I don't have enough room, I'm just gonna go ahead and delete some things. That way we can continue the problem. When you're actually taking the test, you can have some paper and you can do those calculations there, but for the sake of this walkthrough, this is how we're gonna do it. So we want tons, but we're in cubic feet. And we're given a density of about, let's see, 80 pounds per cubic foot. So let's use that to our advantage. We need to recognize that this question is really just testing our ability to convert units. So there's likely a relationship we can use here, and it looks like there is. It looks like some outside knowledge that you might need is that in 1 ton, there are 2,000 pounds. All right. So knowing that, what I'm going to do is I'm going to say 80 pounds per cubic foot. And I know there's 2,000 pounds in 1 ton. And by doing this, what I'm going to get is I think I'm going to be able to have a factor that I can do some manipulation with to get my answer into tons. So pounds are going to cancel, and I'm going to be left with tons per cubic foot. And so when we do that math, we come out with 0.04 ton per cubic foot. And that's exactly what I want, because if I divide this entire large number by 0.04 ton per cubic foot, what happens to the cubic feet units cancel out and I'm left with tons, and I know I've gotten the right answer. So when you plug this in and you divide by 0.04 and your cubic feet cancel, you get 34,848,000, which is answer D. All right. At first, I kind of thought that I was going to need to know something about lignite, but it really just looks like this was some dimensional analysis, really. All right, wasn't too bad. Moving on to number 6. The scale for describing the effects or damage caused by an earthquake at a given geographic location is called the what? Right off the bat, I don't know what a Bernoulli scale is. Never heard of it. I've heard of the Bernoulli principle, and I've heard of the Bernoulli distribution in mathematics, but I've never heard of a Bernoulli scale, question mark. So let's go ahead and move on. Maybe that's the right answer, but I won't really know for certain unless I know that the other 3, if I'm familiar with the other 3 and I know that they don't match this description. So let's go ahead. B, a Richter scale. I do know what that is, and I know that that measures earthquake strength. All right. Modified Mercalli scale. So that scale measures intensity of shaking based on how much damage happens in an area. So shaking intensity. I don't know. Whatever. And then D, moment magnitude scale. Well, that uses the measure of an earthquake's magnitude based on its seismic moment. So it looks like I don't need to know what a Bernoulli scale is. That's probably like a trick question or trick answer. I'm pretty confident that it's the modified Mercalli scale is most clearly this description. So I'm going to go with A. Okay, so number 7. Which statement best describes the effect of diagenesis on the overall quality of an oil gas reservoir? Immediately, yikes. Petroleum geology, ugh, not my area of interest, and I've never taken a course on petroleum geology, but I am a geologist, and I recognize that as a geologist, I have a lot of tools at my disposal, and oftentimes you don't need specific knowledge to answer problems. It's all about interpretation and going with what your data says. So let's go ahead and take a look at the problem and see if we can figure it out. So the answer choices: diagenesis enhances, diminishes, enhance or diminish, no effect. So to make things easier for me, I'm going to say it enhances, diminishes, it enhances or diminishes, or it doesn't do anything. I think that'll help. So I think it's reasonable and logical to assume that oil reservoirs and aquifers act very similarly, and they must be able to adequately store and transmit and accumulate either petroleum or water in the case of an aquifer. So therefore, permeability and porosity have to play a role. And diagenesis, which is what we're talking about here, is just the alteration of rocks post-burial. And diagenesis has the ability to produce secondary porosity through things like compaction, cementation, replacement, things like that. And diagenetic processes, they generally decrease. So my first instinct would be D, that they diminish reservoir quality. But there are cases of replacement, specifically one that's coming to mind is called dolomitization, which is where we have the replacement of calcium in a limestone with magnesium. So we're changing limestone to a dolomite. And when we do that, because of the ionic radii of those two elements, that's going to increase pore space. So in essence, increasing the quality, increasing permeability and porosity, and thereby increasing our quality of our aquifer, or in this case, our reservoir. So I can think of both situations where diagenesis improves and or enhances and diminishes reservoir quality. So I know that there probably is more that I'm not thinking of, but the mere existence of one of each, I can say C is correct. Okay. D, incipient lateral displacement across a narrow zone is often defined by the appearance of rhytal fractures on the ground. Two typical patterns of a rhytal fracture are shown in figure 24. With respect to the pattern shown, A is right stepping, indicates right lateral movement. Okay, so rhytal shears, also known as R shears. So let's talk about what it means to be right stepping or left stepping. So here in the corners of this page, I'm going to write, so right stepping in echelon faults go in this direction, all right? Where left stepping go in this direction. Hopefully that visual helps. And so let's go ahead and determine which direction each of these are stepping. So this is right stepping, and this is left stepping. Okay, so let's see. A is right stepping, B is left stepping. That's true. A is right stepping, indicates. So I know right off the bat that D is wrong because they're both not right stepping. A is right stepping, that's true. It indicates right lateral movement. So that is wrong. And the reason that's wrong is because rhytal fractures indicate relative movement. So rhytal shear faults, they step in the opposite direction of the sense of movement. So a right stepping rhytal fracture is going to indicate a left lateral movement, whereas a left stepping rhytal fracture is going to be indicating a right lateral. So this would be right lateral and this would be left lateral. So we have to match them up. So left, this is going to be, I'm going to do right lateral, and this is going to be left lateral. So A is right stepping, indicates a left lateral movement. That is true, but let's go ahead and prove it to ourselves. B is left stepping and indicates vertical movement. No, because we know what the sense of movement is. It's not vertical. A is right stepping, indicates a right lateral movement. We know that's wrong because it's right stepping, it has to be showing an opposite direction for the sense of movement. So we know that our answer choice has to be C. Okie dokie. Let's move on to number 9. The rate of production from a subsurface reservoir is most directly related to what? So my first question is, what are we producing? What does product mean? And for me, that means getting something from the reservoir. And in this case, how well something is going to be flowing. And that's going to be our ticket to getting the more of the substance that we want. And so the geology word for that is permeability. Okay. Number 10. What is the best radiometric dating technique to determine the age difference between two Miocene-age volcanic ash deposits separated by 500 feet vertically? Whew, that's a mouthful. Well, what do I know about these different dating techniques? Well, I know potassium argon is used for things like age of mineralization, evaporite formation, determining cooling histories of metamorphic and igneous rocks. So that seems promising. I also know that it has an age range, a pretty long age range from like a few thousand to like 4.5 billion years. So that seems pretty reasonable, but I'll come back to it. Carbon, so we're looking at organic material with like a really young age range, about like 50,000 years. So that's not in our age range. So if, just in case we didn't remember, I'm going to put it up here. But the Miocene, that range is 23 million years ago to like 5.3 million years ago. So definitely not B. Uranium lead. So we use that for things like carbonates, opals, fossils, minerals that have a high uranium content. Also has a pretty large age range similar to potassium argon. But that just doesn't seem, I have an argument that's better for potassium argon than uranium lead, and I'll get to that in a moment. And then the fission track uranium, which this is referring to, we use this for dating zircon, mica, tektites. We use it for cooling ages. Doesn't really have that long of an age range comparison to potassium argon, probably like 100,000 to about 20 million years. So maybe not even in our age range or a viable option for us. But here's my argument for potassium argon. So potassium argon can be used to date really old things, and it has an application in dating old volcanic rock, which we're looking at volcanic ash deposits. So I feel really good about this. And I feel very confident in my answer here because I know that potassium 40 and argon 40 are going to be present in erupted lava. And I know that because argon 40 is a noble gas, it's not going to bind to anything, and it's going to be released as a gas as the lava cools and solidifies. And that essentially is going to be resetting that potassium argon clock. And we can later use the amount of argon 40 that is available in an solid igneous rock to date it, because all of the other argon 40 will have escaped, and we will have produced more over time through the decay of potassium 40 to argon 40. So I feel pretty confident in saying A, potassium 40 is our ticket. All right, going on to 11. What geophysical method would generally be most effective to map deeply buried bedrock pediments? Ground penetrating radar. Okay, so what do I know? So I know that ground penetrating radar is used to locate and delineate subsurface features, things like storage tanks, buried drums, different types of metallic utilities. Also used to map geologic strata, the groundwater table, but it's really only applicable to depths of like 30 meters or about 100 feet. So that's definitely not in our ballpark. Okay, electrical resistivity. We use that to characterize subsurface hydrogeology. So again, like depth of groundwater, mapping clay aquatards, mapping faults. But I know that for electrical resistivity, you're really, so 18% of the distance between the two dipoles that you're going to be using in the survey is going to be the depth that you're able to survey down to. And that's not feasible for 1,500 foot deep bedrock. So Pretty confident that was not it. Seismic refraction. So things, again, depth of bedrock. This is used for characterizing rock type and degree of weathering, looking at faults, petroleum exploration. But with refraction, the depth that you can see down to is about 1/5 the length of the geophone spread, which includes the offset shots. So if you were looking to get down 10 meters deep, you'll need room for about 50 meters of a spread from the offset shot to the offset shot. So not feasible here either. So D, we'll see. Hopefully we haven't messed up. But with seismic reflection, it's another geophysical method that uses seismic waves. It has a pretty deep investigation depth, and oftentimes down to like 2 kilometers. And so that's definitely deep enough for our application here with the 1,500 feet. So I'm going to say D is our correct answer. Okay. A groundwater model is calibrated when the model grid and layers match the constructed conceptual model. The groundwater flux into the model equals the groundwater flux out. Hydraulic heads and fluxes reproduce the system modeled within an acceptable tolerance. The chosen model boundaries express the nature of the physical boundaries. So a calibrated model is used by hydrogeologists to represent a groundwater system. And model calibration is simply referring to the manipulation of input data in order to improve a model's accuracy, reflecting the observed heads and flows. So I feel like D is not correct. B sounds like a very good answer, especially because we know, if you think on very basic terms, you think input minus output is equal to change in storage. That sounds like a very good answer. But C specifically talks about hydraulic heads and fluxes within an acceptable tolerance. And so what I think we can take away from this is the word modeled means an approximation. And that's what this model is. We are modeling to the best of our ability with an acceptable tolerance, which within a reasonable amount of error are we modeling the system. And so I think C is the best argument. All right. 13, a rock described as Argillaceous contains flattened pebbles, clay-rich, satin luster, composed of coarse mica. So when I immediately think of anything that's argillaceous, I think of an argillaceous shale. So which of these can I associate to a shale? Definitely clay-rich. I mean, even the symbol, if we were going to draw a lithologic symbol, this would be a clay, which would be a shale. So I think this is really just some vocab that you need to know, or know that argilla in Latin means clay, but I don't think that's the best way to remember that. Just associate that with something. So pretty confident. B is our answer. Okay. The creation of new oceanic crust is balanced by the Earth's expansion, the Earth's crust buckling up so the Earth remains a constant size, the equal amount of ocean crust being subducted, equal amount of continental crust being subducted. So first things first, Studies have shown that while the radius of the Earth may be expanding by an incredibly small amount, the Earth is not expanding. I want to entertain C or D. So an equal amount of old ocean crust or continental crust. So when we're talking about new oceanic crust that's being created, it's being created at ridges, right? Mid-ocean ridges. And where does all that material come from? Why are we able to continually make new crust? Well, the material is not going anywhere. It's being subducted elsewhere at subduction zones. And I feel confident that if you're taking this exam, that's something you're familiar with. But this question, I think, is hinting at which is being subducted. So continental crust, is not as dense as ocean crust. So that's why continental continents are able to kind of like float, so to speak, while ocean crust doesn't have that advantage. So it's often subducted. And so that seems pretty plausible that what we're doing is we are destroying old crust and making new crust at ocean ridges. So our answer choice is C. When collecting duplicate samples to validate the quality of laboratory results, the geologist should always identify the duplicate samples, use a sequential numbering system, be sure that the duplicates cannot be identified by the lab, or be sure that the duplicates were sampled at different times. So depending on what your laboratory investigation is, I feel like this could vary a little bit, but don't really have to use a sequential numbering system. So I can think of an instance, for example, if you were looking at strontium isotopic ratios in groundwater, and where you were using those ratios to discern, groundwater or surface water or what have you, if you're wanting to look that signature is able to clearly be identified by your measurement of your sample. And sure, you could label both of your duplicates and, but you would like to be able to, as unbiased as possible, verify the precision and accuracy of your measurements. Especially, are they doing the correct job that you wanted them to? Or, are you able to use that ratio as an accurate identifier and fingerprint for certain groundwater? So taking that into consideration, it's not important that they're duplicated or that they're sampled at different times. They're going to be the same either way. So we can go ahead and mark that off. So if they can't be identified by the lab, I'm assuming that's referring to like a label that will allow us to independently verify the consistency of our results. So C. 16, a stream crosses a strike-slip fault with no deviation in its course. Which of the following statements must be true? The fault is active. The stream crossed the fault since the last fault movement. Strike-slip faults do not affect stream course. Rock units are the same on both sides of the fault. So I know C is not true. I've seen it in person. And I know that, let's see, if if we had some, some surface and we had water running through it, but then one day we see some kind of motion. Oop, that's not good. You'll see a shift in the stream course, but that's assuming that the stream was already there before the movement occurred. So what we can deduce from that is if there's no deviation in the course of the stream, then we know that the stream had to have happened after the movement at the strike slip fault. It doesn't tell us anything about the activity of the fault. The stream crossed the fault since the last movement? Absolutely. And we can be confident it's B, rock units on the same side. No. All right. The horizontal scale of a cross section is 1 to 2,400. The vertical scale is 1 inch equals 1,000 feet. What is the vertical exaggeration? So this requires you to remember that to find vertical exaggeration, you take your vertical scale over your horizontal scale. And in our case, we have 1 over 1,000 and 1 over 24,000. And we want to get rid of these fractions, so we're going to multiply the top and bottom by 24,000. Not doing anything fancy or illegal here. This cancels, and what we get, we multiply this fraction, we get 24,000 divided by 1,000, which when we do that math gives us 24. So we know that our exaggeration is 24 times, and that is option C. Okay. 18. A topographic map shows several circular depressions in a limestone region. What are these features called? Okay, finsters. So finsters, those are windows, quite literally. In German, Fenster means window. Is a window into rocks that underlie a thrust fault. So we know that a kettle is a depression that's in an outwash plain. We see those left behind by glacial retreat. A doline. So a doline is another word for a sinkhole that we commonly use the word sinkhole instead, but they're the same thing. And those are just holes that are formed in karst environments through a couple different ways, but primarily through dissolution or collapse. And we have potholes. So here we're not referring to a pothole like in a road or in a city or somewhere, but rather a hole in a riverbed that's been formed by circular abrasion along a riverbed. So something these all have in common is these are all holes or some depression of some sort. So it's hard to immediately eliminate some things because it's not like we're comparing and contrasting very obviously different things like an in moraine versus some type of dune. Those are very polar opposites. So this makes this question a little bit difficult. So we're looking for a circular depression that occurs in a limestone region. So a finster, that's going to be happening not necessarily in a limestone region. That's just the upthrust of maybe some older units on top of younger units. A kettle, that's like I said, that's glacial environment, that's outwash plain, so definitely not B. A doline, like I said, was a sinkhole, and sinkholes are notorious in limestone regions. So I'm going to say C. I'm not even going to consider D. Plus, I know that occurs in riverbeds. So very confident C is our answer for an 18. Okay. 19. A cross-stratified sand lens that contains thin streaks of mud in the ripple troughs is called what? Lenticular, wavy, graded, flazer bedding. Okay, so this one requires, it seems, a lot more knowledge than some of these other questions have required us. But let's go through what each of these are. So lenticular bedding are isolated ripples of sand that are completely surrounded by mud. Where, so we have, let's see, how should I do this? So we have sand with mud. Wavy bedding is where we have layers, equal layers of sand and mud. So I must just say equal. Graded bedding is not related to either of these other two beddings. Grading bedding is referring to like an increase or a decrease in grain size from the base up. It's like a fining upward sequence or something like that. So it's not similar to these other three. So I'm going to just eliminate that one. And then D, flazer bedding. So that's where we have isolated drapes of mud with cross laminae of sand. So we have mud with sand. And so it appears what we have in similarities between all these is that they all contain, with varying amounts, both sand and mud. So we have to be really specific about what these definitions are and what these these bedding features are when it comes to this question. So a cross-stratified sand lens that contains thin streaks of mud in the ripple trough is called what? So if we have cross-stratified lens, I wrote this down wrong. I was confusing myself. So yeah, so we have sand completely surrounded by mud, where flazer bedding is how I've written this has confused myself. So let me back up. Can I delete this? So what I know is lenticular bedding is where we have a mud matrix with sand. So I'm going to say mud matrix. And then flazer bedding is the opposite. And that's where we have a sand matrix with mud. All right, yes, so that makes sense. So excuse what I said prior. This is actually how it's supposed to be, because wavy bedding is the intermediate between lenticular and flazer. So it's equal parts, equal layers of mud and equal layers of sand. So a cross-stratified sand lens with mud, sand with mud is flazer bedding. All right, last one for this video. In which of the following areas are the largest volumes of andesite lava commonly extruded? Long continental rift valleys. So these questions seem these answers seem very specific, and I do not imagine that The ASBOG exam is going to ask you very specific knowledge or like trivia questions, and that's not their goal. So there's probably something going on here that will make this a lot more simple. So let's just think about this. What is andesite lava? So andesite lava, when I think of that, I think of an intermediate composition. I know it's not 100% felsic, and I know it's not 100% mafic. So what kind of lava would form here? If we have continental rift valleys, we're probably making felsic. Just continental, crust is felsic, so that makes sense. Oceanic lithosphere with continental crust. So oceanic lithosphere, that's mafic. Beneath the continental crust, if you have melting, that could get you an intermediate. So I'm going to mark this intermediate, but we'll look at the other answer choices and see what we get. Within oceanic plates overlying mantle plumes. So mantle plumes are coming from the deep mantle. They have a very mafic chemistry. Again, with mafic, you're just going to have more mafic. Separation, oceanic ridges. Again, just mafic. So it looks like where we're going to get an intermediate composition is going to be where we have some continental crust, some a felsic component, and an oceanic crust, a mafic component. So B. All right, so that's going to be the end of this video. I'm going to upload the other 20 questions, so the other half of this practice exam at a later date. But for now, hopefully this was helpful. If you have any questions, or if I made a mistake somewhere, I think I caught myself up here on 19, but if I didn't catch myself on any errors and these others, please leave a comment, and I'll be sure to make an annotation on the screen and probably leave a comment in the description for people who watch the video later. But hopefully this was enjoyable, and hopefully you got something out of it. All right, we all have a great day. Bye.